Okay, so we're going to pick up where we left off yesterday, and that is talking about vectors. And specifically, how can we do mathematical operations using vectors? So vectors are different. When we do math with vectors, it's different than when we do math with scalars. So as an example of scalar math, let me spell it correctly, scalar. Let's imagine that we're just doing a simple mathematical operation with two numbers, 2 plus 2. Of course, you know that that's 4. When we're dealing with vectors, we could also have two vectors that have magnitude 2. We add those two together, and I can certainly add those two vectors together and get a magnitude of 4, but I can also add those two vectors together and get a magnitude of 2, and I can add those two vectors together and get a magnitude of 0, and many numbers in between. Now, why are these two mathematical operations different? Well, because in the case of vectors, the direction matters. When we add vectors together, you have to take into account the direction of the vectors. So we touched on this in a last class period, how to account for the direction and how to go about adding vectors together. And the way that we do that is we have to break our vectors into components. So if I have a vector A that looks like this, in order to be able to add vector A to another vector, I need to know something about the components of A. I need to know something about the projection on the x-axis A sub x and the projection on the y-axis A sub y. And when I know these components, I can use those components to add the vector A to another vector, say vector B, as long as I know the components of vector B. Now, let's talk a little bit about notation here. When I write down the vector A, like so, usually the way that I write this down is I need to refer to the vector components when I'm trying to communicate the value of this vector. This is one of the ways that physicists and mathematicians treat vectors. So one way that I could write this number down, this vector down, is A sub x, which is just a number. I'm using letters here to be general, but this is just some number. It's a magnitude. And then a direction, and I'll call that the x direction, because ax is along the x direction. And I add to that A sub y, which of course lies in the y direction. And this is kind of ugly. It's kind of a pain in the butt to write this. So we have a shorthand notation that allows us to write this a little bit more clearly. And that is to make use of something called unit vectors. So that's what I'm doing right here, is I'm writing these weird I hat and j hat characters. And those two characters, I hat and j hat, are called unit vectors. I hat and j hat, and I should say k hat, if I have 3 dimensions, are unit vectors. Okay, and what is a unit vector? Well, a unit vector is, it's a vector that has a dimension of 1, a magnitude of 1, which is important because each of our unit vectors then doesn't actually change the magnitude of the vector itself. If I multiply 1, which is inherent in this I hat, times ax, ax still has the value of ax. Right, so a vector that has a magnitude of 1 and a direction that is parallel to one of the coordinate axes. And of course, in the case of I hat, then we associate I hat with the x-axis. So I hat tells us that as a unit vector that has a magnitude of 1 and it's parallel to the x-axis. J hat is parallel to the y-axis, and k hat is parallel to the z-axis. Right. So these unit vectors then are nothing more than a way that we can efficiently and compactly denote vectors. It's simply a notation. And so if I assign numbers to each of these things, so let's just say ay is equal to 5, ax is equal to 3, and we'll say az in this case is just 0. We just have a two-dimensional vector. Then I can write this vector down in this form as ax is equal to 3 in the I hat, and then ay is equal to 5 and that's in the j hat, and then of course if I want to be explicit about it, az is 0, and that's in the k hat. So now I have a way to completely denote my vector a using a pretty compact notation. Instead of writing x dir, y dir, z dir, I just use I hat, j hat, and k hat. All right, so once I know how to write down the vectors in an appropriate manner, I can start to do some mathematical operations on them. So let's take a look at a couple vectors, and we'll do this again in the general case, not using numbers, and then we'll do an example in just a minute. So imagine that I want to add two vectors, a and b, and those vectors are two-dimensional. They lie in the x and the y direction. They lie in a two-dimensional plane. So I can write that down using my I hat, j hat notation as ax plus bx in the I hat plus ay plus by in the j hat. So notice what I've done here. To add two vectors together, I don't just add the magnitudes of these two vectors, I add the components of the vectors. So ax and bx are added, and that's kept separate from ay and by. And so what I'm left with is some vector that has a term, a component in the x direction, a resultant vector that has a term in the x direction and the I hat direction, and a term in the j hat direction. Similarly, I can do subtraction. And when I'm doing subtraction, you want to note that this is equivalent, a vector minus b vector is equivalent to a vector plus the opposite of b vector, right? So what I get then is something quite similar to my above equation, where I get ax minus bx in the I hat plus ay minus by in the j hat. So this is the general form of how we write down vectors and how we do vector math. All right, so let's go ahead and do a bit of an example adding vectors together. We'll do more than two. We'll actually do 4 vectors. So we're going to do this example involving Bob. So we have after a night out at the corner brewery, some of you may know, Bob stumbles home and wants to get to his bed, which is 4 meters east of the door. But in order to get there, he kind of wanders a bit. All right, so let's draw a picture, because that's what we should do every time we solve a problem. So here we have Bob standing by the door, and 4 meters away is his bed. Really simple drawing. Now, in order to get to his bed, Bob takes sort of a strange route. So I'm going to write this down in terms of 4 different vectors, because that's really what he's doing. He's moving a bit, so his movements have a magnitude, so some distance that he traveled, and a direction. So he starts off by moving 1 meter at 30 degrees south of east. I'm going to call that vector B, or vector A. Vector B, then after that he moves 2 meters at 10 degrees west of north. After that he moves 1.2 meters and he goes due east. And then after that he goes 0.8 meters at 70 degrees south of east. All right, so he has 4 segments, and I want to know how far away from the bed is he? Does he make it to the bed? So let's sort of label these vectors on my picture. So he starts off moving 1 meter a bit south of east, 30 degrees south of east. So that must look something like this. I'm going to call that vector A. I'm not going to label the angles here or anything like that. We'll just make it kind of a general picture. After that, he goes 2 meters a little bit west of north. So that would be something like this. That's vector B. Give that the A vector sign. Then he moves due east, so that one's pretty easy, just straight line like so. And then he moves a bit south of east, so 70 degrees south of east is going to be something like this down here. And that's vector D. So the question is, I want to know, does he make it to the bed? And I can't tell by looking at the picture. All right, so in order to look at this problem a little bit more closely, what I'm going to do is draw these vectors separately, just so we can really be clear about what we're doing here. So here's my vector A, and then I have my vector B. I'm going to draw them separately, and you'll see why in a minute, because I'm going to break them up into the components. my vector C, that one's pretty easy. Straight east, and then vector D, something like this. Now I have some angles here. Let me draw those angles. And vector 1 is 30 degrees south of east. So 30 degrees south of east, that's this angle. 30 degrees. Vector B is 10 degrees west of north. So that's actually this angle right here. That's 10 degrees. Vector C is due east, so there's no angle I need to worry about there. And then vector D is 70 degrees south of east. So that's going to be this angle here. Okay. So what I'm doing here is now I need to break up these vectors into their components. So in order to do that, I need to define a coordinate system. I'm going to use my standard horizontal and vertical x and y coordinate system like so. I'm just going to label that so we know, so we have something to reference against. So that allows me to define vector components for each of these vectors. So I start off, I'm looking at vector A here. And I want to know the x and y components. I want to know the length of this side, which is ax, and the length of that side, which is ay. Similarly, for vector B, I want to know this side, which is bx, and this side here, which is by. Vector C only lies in the x direction, so this I can write as cx, but it's the same as the length of C is the same as the magnitude of C. This length of cx is the same as the magnitude of C. And then cy is 0, so that one's really easy. And then D, I want to know dx and dy. All right? So I need to use my trig formulas to figure out the components of each of these 4 vectors. So I can do that pretty easily. We'll start off with vector A, and we'll just sort of go down the list. So ax. I know this angle right here, 30 degrees. That looks like the angle, this AX side is adjacent to the angle 30 degrees, which means I'm going to use cosine. So I'm going to get, this is going to be 1 meter times the cosine of 30 degrees. And if you do the math really quickly, you should see that that's 0.87. AY then must be 1 meter times the sine of 30 degrees. If you do the math there, the sine of 30 is 1/2, so this is 0.5 meters. All right, but you have to take a look at something really quickly. AY is going downwards, so if I start from here and look at my vector, it's going down. AY is actually going from the origin, which would be this spot, downwards. But I've defined y to be positive upwards, so that means that this number has to be negative. Right, because it's going downwards, and I should have put a negative sign here just to reinforce that. That's obviously really important because eventually I'm going to add up all my components, all my y components, and if that's not negative, my answer is going to be wrong. So you need to make sure when we're defining our angles and when we're calculating our components that we're taking into account our original definition of the coordinate system, our x and y coordinate system. All right, so we've done x and A now. Let's start to work on B. So bx is going to be this side of the triangle, of the right triangle. But you notice now that bx is actually the opposite to the angle that we're given, this 10-degree angle. So I don't use cosine, I actually use sine. So this is going to be 2 meters times the sine of 10 degrees. Just like I said earlier, it's not always cosine that is associated with the x direction. It just depends on which angle you're given. And if you do that, you should see that that's equal to 0.35 meters. Again, x now is pointing to the left. That is the negative direction, so I need to stick a negative sign there. by is equal to 2 meters times the cosine of 10 degrees. If you solve for that, you get 1.97 meters. My x and y components of C are very simple. Cx is just equal to the magnitude of C, which is 1.2 meters, and then Cy is equal to 0, like I said before. And that just leaves us with dx. We have this angle, and dx is adjacent to that angle, so we're going to use the cosine for the x direction, 0.8 times the cosine of 70. That's equal to 0.27 meters. And then dy is equal to 0.8 times the sine of 70. And that's going to be equal to 0.75 meters. And again, dy is pointing down from the origin. That means that's got to be negative. All right, so I've done all the hard work here. I've broken up all my vectors into their components. Now I just need to add them together to get my final vector. I'm going to call that final vector capital R for resultant, because that's what I'm doing, as I'm figuring out what the resultant vector is when I add all of them together. And just to summarize, if you remember, I'm just going to add together all the individual components of the vectors and stick a unit vector in the end of that. So it's going to look like this: ax plus bx plus cx plus dx. That's all in the y direction, in the I hat direction. And then I'm going to add together ay plus by plus cy plus dy. And that's going to tell me the length of the side of the resultant vector's y component. So if I do that, ax is 0.87 plus or minus 0.35 plus 1.2 plus 0.27. What I get is 1.99 meters in the I hat direction. And then in the y direction, I get negative 0.5 plus 1.97 plus 0 minus 0.75. The answer that you'll find in the y direction is 0.7 meters. And then I stick that a j hat on there. So what I've found here are the components of my resultant vector. All right, what I've actually found here, let me go up here and draw it. What I've solved for is this guy right here. I add together all the vectors, so I start from the start of the first vector and I end at the end of the last vector. That is my resultant vector. All right, I'm going to redraw that. Obviously, it is not to scale. All right, really what I have is this. This is R. And R has an x component that is 1.99 meters long and a y component that's 0.7 meters long. Okay, so at this point I can sort of make a conclusion about whether or not Bob reaches his bed. And remember I said that the bed was actually 4 meters away, so the bed's somewhere like out here. And he only made it just about 2 meters towards the bed. The y direction doesn't really matter. The bed's probably longer than a meter, so in the y direction he didn't go too far in the y direction, but he didn't go far enough in the x direction. So it looks like he didn't actually make it to the bed. So no, he didn't make it. But let's take this one step further just to finalize this problem. Sometimes what you'll be asked for, what you'll be tasked to do, is actually tell me about the magnitude and the direction of the resultant vector, not just the components. So if I want to write down the vector r, I need to know the magnitude. Right? So well, how do I find the magnitude of this? I know the magnitude of vector r. Well, it's pretty simple. We have a right triangle here. We have the two sides of the right triangle. We're looking for the length of the hypotenuse. So all we need to do to get that is take the square of the sides and add them together. So we're going to take 1.99 squared plus 0.7 squared, and then take the square root. If you do that calculation, you should get 2.1 meters. So that's the magnitude of vector r. The last piece of the puzzle that I might be interested in is what is this angle theta? Right, so what is the angle, in this case, from the positive x-axis? And to figure that out, well, I've got all three sides now. I have this side, and the hypotenuse. So I can use any trig identity that I want. I'll just pick the inverse tangent because that'll tell me theta. Actually, let me give myself a little bit more room. I'm solving for theta, so theta is equal to the inverse tangent of the opposite side, which is 0.7 meters, divided by the adjacent side, 1.99 meters. You do that calculation, something like 19 degrees. All right. So we have another perfectly acceptable way to write down the magnitude of, to write down the value of a vector. We have what we've written here is a vector in terms of its magnitude and its angle. And so we can write that down using r vector is equal to 2.1 meters at an angle of 19 degrees. In this case, it would be from the positive axis, or since we have directions, that would be north of east, just because we've defined those in the problem.